Now, next, after talking about force, fields, then a concept which helps us relate those quantities. After that, we are going to talk about energy. And we are going to define everything from the very basic. From a simple formula, we know that work is done. The formula for work is simply F dot ds or F dot dr. And if force at different places is different, then it can be written as work done is force dot dr. So this is a new chapter named as electric potential and potential energy. And we are going to see what these two terms mean and also derive them from the very basics. A little bit of integration is required here, because as you can see, the formula for work done holds the integration sign. So suppose you want to create a system. So if you want to create a system which consists of two charges, first charge, let us say, has charge Q on it, and there is another charge which is Q naught. So this is a simple system in which there are two charges, and these charges, they are separated by a distance of r. So if I ask you, what is the energy required to make this system? The question is, what is the energy required to make this system? What is energy required to make this system or to build this system? So the question before that would be, Miss, how would you build this system? There are only two particles, so it's very easy to do. Means first, what you will do, you'll bring in first particle. You'll bring in first particle. And see, if there is a single charge, you can move it anywhere. If we are ignoring the gravitation, of course, you can move it anywhere without much difficulty. A single particle, it won't offer any resistance. You can just pick it up and place it anywhere. So I'm placing it at point A. I'm placing the first particle at point A, and I need to place second particle at point B. Now, if you want to place the second particle at a distance r away, it will offer a resistance, because if suppose your particle is here very far away, particle Q naught is very far away, then charge Q will apply a force on it. Charge Q will apply a force on it, which will be away from the original charge. And to counterfeit this force, to move it in this direction, you will apply a force which will be in such a way such that it moves from the point C, which is at infinity, which is almost at infinity, to point B. You want to move it in this direction. So this is the initial position of the point of the charge. This is the final position of the charge. You want to move it from infinity to the point B. So to make this system, you will first place the first charge, no resistance, no work done, no forces required for it, just place it there, assuming that the gravitational force is zero. But to place the second charge, you have to pick it from infinity, and you have to move in such a direction such that it goes from infinity to point B. Okay, So I will call this force as the external force. This is the force applied by external agent, force applied by you. External agent. So to calculate the work done by external agent, I can simply integrate this force by external agent into the displacement, call it dx. So force is along this direction and you want to move it from point C to B. So let us call this general distance as dx from here to here. Let us call this as x. And a very small displacement is given to it, which has a value of dx. Now let us calculate this force. The value of the force can be given. Value of the force is given. See, this is electrostatic force. F is electrostatic force. That will be given by 1 by 4 pi epsilon naught into q naught by x. Okay, and you just want to overcome this force. Your force should be very small amount greater than the F. So you want to move, q naught should be moved very slowly, such that F external is approximately equal to F, but a little greater than F. The external force should be a small amount greater than F, but it should be moved very slowly. If the force is large, then this charge will have a kinetic energy. If this charge has a kinetic energy, then it will keep on moving. I just want to place it here, not want this charge to have a velocity. So Q naught charge should be moved very slowly, and F external is equal to F. In that case, we can write F external is equal to F. I can put this value here. So work done by external agent would be this Q naught upon 4 pi x epsilon naught. Instead of F external, you can put this value divided by x, and F and dx are in the same direction. But see, you're moving the dx in this direction. This value of dx in this direction, that is opposite to the direction of x. Okay, so because of dx, x is decreasing. X decreases along dx. So that's why you should put a negative sign here. You should put a negative sign here. Force is q naught by x squared. Because x decreases along dx. Now let us integrate this. Q naught by 4 pi epsilon naught. This will come out of the integration. That to integrate this minus dx by x squared. This will be from point C to B, from infinity to point B. The integration will be from infinity to point B. Integration of minus 1 by x square is 1 by x. At B, the value of x is, see, at B, the value of x is r. And at C, the value of x is infinity. So this will be q naught upon 4 pi epsilon naught into 1 by, at B, the value is r. So 1 by r minus 1 by infinity. If you divide a number by infinity, it will be 0. So your final result is the work done by external agent in bringing the charge from infinity to point B is q naught by 4 pi epsilon naught. This is what you have calculated. The work done is positive. Of course, the force is in direction of the displacement. So work done should be positive. Okay. This is the work done by external agent. If you want to calculate the work done by electric field, so that will be C. The force is the same, but force is along the right and displacement is along the left. In that case, you will write the work done by electric field will be q naught by 4 pi epsilon naught r, but with a negative sign. This is the work done by electric field because force is along right. Force due to electric field is along the right. And force of electric field or force by charge q is towards right, and its displacement is towards left. So work done will be negative. Its displacement is towards left. Okay. Now, also, if you apply the work energy conservation, so we can write work done by external agent plus work done by electric field. There are no other forces. There are only two forces. So work done by external agent plus work done by this electric field. Work done by electric field, force by electric field. This should be equal to 0. This is your work energy theorem. Or also, see, you can write work done by external agent plus work done by electric field, or the sum of all the work done is equal to change in kinetic energy. Okay, but in this case, change in kinetic energy is 0. In this case, change in kinetic energy is 0. Also, this is a conservative force. Because this is a conservative force, you can write work done by external agent is equal to change in potential energy. What this means is that work done by external agent is stored as potential energy. Work done by external agent is stored as potential energy in the system. Given change in kinetic energy is 0. If there is no change in kinetic energy, then whatever work done is done by you on the system, it will be stored as the potential energy. Okay, so this has a limitation. This line has a limitation. This only holds true when kinetic energy changes 0. But this relation, see, all this comes from mechanics. Work done by conservative force. So here electric field is conservative force. Is negative of change in potential energy. And this holds for all conservative forces. This is true because electric force is conservative force. Electrostatic force is conservative force. All these things are told in detail in 11th standard, but here also I'm telling you, conservative force is conservative force. Okay, I'll go through all the things again. You want to build this system. To build this system, you need to bring two charges at a distance r. Bringing the first charge does not take any effort. But bringing the second charge from infinity to point B, you'll have to push the charge from point C to point B. So you are an external agent here. The external agent, it will be resisting the force by electric field. But I want to do this thing very slowly because the charge should not move. The charge should be moved very, very slowly. It should not gain any kinetic energy. So external field is force by external agent is approximately equal to force by the electric field. Okay, this is force by electric field. Force by Q on Q naught. So work done by external agent is force into displacement integrated. So but external agent force is equal to electric field force. So I can put it here. I put a negative sign here because as x decreases along the value of dx, means dx is decreasing the value of x. Solving this, we get this value. This is work done by external agent in bringing the charge from infinity to point B. This is work done.
Yes.
Yeah.
Sir, will charge A naught, sir, will charge Q naught move when Q naught is moving?
No, charge Q is fixed at its position. It's fixed at its position. It is not moving. So what is W external? Work done by external agent in bringing charge Q naught from infinity to point B. And using this, you can also calculate the work done by electric field, because work done by electric field will be just the negative of work done by external agent, because force here is opposite to the direction of displacement. So we get work done by electric field is minus of Q naught by 4 pi epsilon naught R. After this is done, we are using a little bit of work energy theorem. We know work done by external agent plus work done by electric field is equal to change in kinetic energy. In this case, change in kinetic energy is 0. So we get work done by external agent is equal to negative of work done by electric field. Also, from mechanics, we know that work done by external agent is equal to change in potential energy. Work done by whatever work you do on the system is stored as a potential energy in the system, given that change in kinetic energy is 0. Also, work done by electric field is equal to negative of change in potential energy, given this is when you're talking about conservative forces, and electrostatic force is a conservative force. Any questions about this?
No, sir.
Okay. Now see, what you have to remember from here.
Sir, 1 minute.
Yeah.
Okay.
Yeah, noted. Now we have found out that work done by external agent is stored as potential energy. So simply, if you want to make this system of two charges, Q1 and Q2, which is separated by a distance R, then the amount of work that you have to do, that will be work done by external agent will be to make this system. To make this system, we have calculated it to be Q1, Q2 by 4 pi epsilon naught R. This is work done by external agent. And if kinetic energy is 0, then work done is stored as a potential energy. Work done by external agent is stored as the potential energy. So we can write work done by external agent as Q1, Q2 by 4 pi epsilon naught R, and change in potential energy, that will be final potential, this potential minus initial potential. Okay, final potential minus initial potential. Delta U means change. Change means final minus initial. So final is this is the potential energy of the system. Final is the potential energy of the system. And initially, both of the system were at infinity. So their potential will be 0. At infinity, the potential energy will be 0. The potential energy of the system is 0. From here, we come to the conclusion that potential energy of a two-particle system in electrostatics, that is equal to Q1, Q2 by 4 pi epsilon naught R. This is potential energy of a two-particle system. Potential energy of two-charge system, two-point charge system separated by a distance R. Separated by a distance R. That's the first thing that you have to memorize. And of course, we have done it from the very basics. All the calculations are done from the basics. So you have to understand that too. So if two charges are separated by a distance R, then this is called the potential energy of the system. And now we have learned enough to define the electric potential energy. So we have just defined the value. What is the electric potential energy? So electric potential energy will be defined like this. The electric potential energy of a system of charges electric potential energy of a system of charges. We have only derived formula for two charges, but we are writing the definition for a general system. So electric potential energy of a system of charges is the work done in bringing those charges from infinity to near each other to form a system. So you're picking up individual charges and you're placing them near each other to form a system. And that is the definition of electric potential energy. That is the definition of electric potential energy. Any questions in here? Note it down. So for potential energy of a 2.2 charge system is already derived. The formula is derived. And for other systems, I'll tell you the formulas. Now see, this was for a 2 charge system. Suppose we have a 3 charge system. Question is find potential energy of the system. And the system is, let us say like this, 3 charges, Q1, Q2, Q3, and they are along the sides of an, they're separated by a same distance r. So this is an equilateral triangle. So potential energy in this case is simply written as sum of all the pairs. Potential energy as sum of all the pairs. So here you'll write the total potential energy as potential energy of the first and second charge system plus potential energy of the first and third charge system plus potential energy of the second and third charge system. So that will give you Q1, Q2 by 4 pi epsilon naught R plus Q1, Q3 by 4 pi epsilon naught R plus Q2, Q3 by 4 pi epsilon naught R. You simply add the individual potential energies of two charges. They will come in pairs. And suppose you have a pair like this. You have the system of charges like this. There are 4 charges. And they are on the vertices of a square, the corners of a square. The square of side A. So here there are 4 charges. You will be writing all the possible pairs. If there are 4 charges, number of pairs is 6. The first with the third, second one, this one, and this one. Okay, so there are 4 pairs which are separated by distance A. So for that, the potential energy between these two charges will be Q square by 4 pi epsilon naught A. And like this, there are 4 pairs, 1, 2, 3, and 4. So adding 4 times, that means multiplying by 4. Plus, there are 2 charges which are separated by a distance of A root 2. They are separated by a distance of A root 2. So Q square by 4 pi epsilon naught A root 2. And there are 2 pair of charges like this. So adding 2 times means multiplying by 2. So this will be the total potential energy of the system. I can take Q square by 4 pi epsilon naught A common. And I'll get 4 plus root 2 in the bracket. So what you have to do, you have to take each and every pair and add the potential energy, individual potential energy. Students, do you have any questions? Any doubt?
No, sir.
Okay.
No, sir.
Okay. So this is how electric potential energy of 2-point charges and of a system is defined. After defining electric potential energy, we have a quantity which is much more useful than the electric potential energy. And that is called electric potential. First, I will define electric potential. And you'll see that is a much easier concept to understand. Before it was electric potential energy. Here it is only electric potential. So this is defined like this. electric potential is the work done by an external agent in carrying a unit positive test charge from infinity to a point P, or from infinity to a point in electric field. This is the definition of electric potential. Now, work done in by external agent in carrying any charge that we know. So, what is that work done? The value of that work done was work done by external agent in carrying any charge. That was Q into Q naught by 4 pi epsilon naught R square. Okay. Here, of course, we are deriving it for a two-particle system, two-point charge system. Then we'll generalize the formula to all the other types. This is a two-point charge system in which, of course, there are two charges, Q and Q naught, and they are separated by a distance of R. So work done by external agent in bringing this system was Q naught. But if you want to find the work done by external agent in carrying a unit positive test charge, let us say Q naught is your test charge. If Q naught is your test charge, then you can calculate per unit work done by just dividing it by Q naught. That will give you a value of Q by 4 pi epsilon naught R, not square, but R. So if you divide the work done by Q naught, you're basically counting work done per unit charge. If this was work done by Q naught amount of charge, then work done by 1 unit of charge, work done or in moving 1 unit of charge will be work done by Q naught. And this is defined as the potential. This is the potential. Q by 4 pi epsilon naught R. So
That Q naught is 1, huh?
yeah. No, Q naught can have any value. But yeah, if Q naught has 1, then see earlier Q naught was having any value. Here your Q naught is having 1 unit of charge. It can be 1 coulomb.
Because it is unit positive test charge, so Q naught will be 1.
Yeah. In that case, the potential becomes Q by 4 pi epsilon naught R. So what this means that charge Q is giving a value of potential this much amount by. Okay, this is potential of point P. V is potential of point P. Point is just point. There is no charge over here. P is potential of point P due to charge Q. Charge Q. Now the benefit of this is instead of placing Q naught, if suppose you can place any other charge. Okay, this is potential of point P. Potential of point P due to charge Q. Now, suppose if you want to find the potential energy of the system when there are two charges, first is Q and At point P, we have another charge, let us say Q dash. So you can just multiply the value of potential by the charge to get the value of potential energy, right? Because potential energy will be potential, that is Q by 4 pi epsilon naught R into Q dash. So you can multiply potential at a point with charge kept at it, with charge kept at the point to get potential energy. So when you multiply potential of the point with the charge that you are keeping there, you can get potential energy. So you can keep any charge, Q dash, Q1, Q4, 1 coulomb, 5 coulomb, and you can calculate the potential energy using that relation. So just remember this relation, potential due to a single point charge. Now, if I want to write the SI units, so potential is work done per unit charge. So unit will be joules per coulomb. And for potential, it is just potential energy, it is just joules. Unit of potential energy is just joules. Now, if we take some examples, we'll understand this in a much better way. So I'll give a simple question, find potential of point P. Find potential at point P. Of course, we are studying electrostatics. So potential means electric potential. Okay, this potential means electric potential. And I'll give the first system like this. This is a charge Q. And this is your point P, which is R distance away. So potential of point P will be simply Q divided by 4 pi epsilon naught R. This is what we have derived for this. Potential of point P will be Q by 4 pi epsilon naught R. But if suppose there are multiple charges, there are two charges, let us suppose both of them are Q, or I can write Q1 here, Q2 here, and you want to find potential due to P, potential at point P. So this will be equal to potential due to Q1 plus potential due to Q2. That will be Q1 by 4 pi epsilon naught R plus Q2 by 4 pi epsilon naught R. Okay, so see, potential energy is a scalar quantity, and potential is also a scalar quantity, as it is work divided by charge. So potential is a scalar quantity. So you can simply add even potential energy, that is an energy, so that is also a scalar quantity. I'll give you another problem to practice right now. So let us say the system is like this. There are two charges. Call this as Q. This is also Q. And the point P is here. Find potential at point P. Solve it and tell me the answer. That is correct. Yeah. So you can simply write 2q by 4 pi epsilon naught r. That is just added like scalars. Next, suppose you have charges arranged like this. And consider this as two equilateral triangles. One is on the upper side, one is on the lower side. Charge here is Q, Q, and one of the charges minus Q. If the charge is minus Q, just stay in the formula, take minus Q. That's all. Find the potential at point P here. Find the potential at point P.
Sir, same.
Tell me the value.
Q by 4 pi epsilon r.
Yeah. So for the first charge, you can take this for electric potential due to this will be Q by 4 pi epsilon naught r. Plus electric field due to this, electric potential due to the second charge is Q by 4 pi epsilon naught r. And the third one, it will have a negative. So this cancel out each other. And you have remaining as Q by 4 pi epsilon naught r. So we have found that potential due to a single charge system, potential due to a point charge, is given by V is equal to Q by 4 pi epsilon naught r. And potential is of a point. Potential is of a point. If the point is different, then R is different, then potential will change. And suppose for a point charge, you want to write, you want to draw the graph between potential and the versus the distance. So there is an inverse relation. So as R increases, potential will decrease. And suppose there is a distribution of potential, as in there is a line charge. We'll do a small example, so it's not really important for you, but let us understand this. Suppose if there is a continuous charge system, continuous charge system. Let us say there is a rod, positively charged rod, call the length to be L. There are two sides A and B, and it is positively charged. The charge per unit length is lambda, and I want to find the potential at point P, which is x distance away from the end B. So what I know is a potential due to a single point. Potential due to a single point. So what I'll do, I'll simply take a point. This a point, which is, let us say, r distance away. Let me write this as r. So L and R are fixed. I will take a point charge. Let us say the charge on this is dq. Charge on this is dq. And the distance between these two is x. So length of this will be taken as dx. So the small charge dq, due to this, I know what potential it will give at point P. That will be simply dq divided by 4 pi epsilon naught into the distance x. That is potential due to this small charge, point charge. Dq is very, very small. The length of dq is dx, that is very, very small. So this is the value of potential at point P due to dq. This is potential at P due to dq. If you want to find potential due to all the other charges, so you'll have to integrate. So you will write V is equal to integration of dq divided by 4 pi epsilon naught x. But I have to replace dq and write it in terms of dx. So I know lambda is charge per unit length. Lambda is dq by dx. So dq can be written as lambda into dx.
Sir, dx is small length now.
dx is small length, yeah, length of the charge. You can put it here and do the integration. Lambda dx upon 4 pi epsilon naught x. I can take lambda by 4 pi epsilon naught outside the integration. And see, the limits will be from r, the nearest charge is r distance away, and the farthest charge is r plus L distance away. So I'll write this as r, and this is r plus L. Integration will be from r to r plus L. Integration of 1 by x is log x. So lambda by 4 pi epsilon naught ln x, the lower limit and the upper limit, r plus L. If you calculate, you'll get the value as lambda by 4 pi epsilon naught log of r plus L by r. So we took a simple example for a continuous charge system. And the value of potential is again positive because it was a positive charge. So while doing the integration or while finding the potential of a continuous charge system, first you will take a point. And that point is, let us say, x distance away from point P. Then we can write electric field due to a single point. If that is electric potential due to a single point, if that is found, you can integrate it to find the electric potential due to all the charges on the continuous body. Any questions on this?
No, sir, but could you please wait for 1 minute?
Yeah, please note it down. It's the work done by an external agent in carrying a unit positive charge from one point to the other point in an electric field This is called the potential difference. That is the work done by an external agent in carrying a unit positive charge from one point to the other point. For example, if you have a charge Q and the potential around it will be, let us say, at point A, or from point A, you want to move the charge Q naught to point B. So you can define work done per unit charge, that will be equal to work done, of course, external by Q naught, will be equal to potential at A minus potential at B. This formula comes from definition only. Potential difference, that is VA minus VB, because charge Q naught is moved from A to B. Q naught is moved from A to B. To give you a simple example, I will solve a question. Suppose there is a charge Q and you want to find potential difference between point A and B. So let us say this distance is, call it R. And this distance is also R. So I can write, see, potential at point A, that will be Q by 4 pi epsilon naught R. And potential at point B will be Q by 4 pi epsilon naught into 2R, because the distance of point B from the original charge is 2R. If you want to write the potential difference between point A and B, that will be VB minus VA. This is the potential difference. Potential difference, that is VB minus VA. So final potential minus initial potential. This, see, the calculation part is really easy. You just calculate the final potential, then the initial potential, and they will get the value of the potential difference. Okay, and this is equal to the work done by external agent per unit charge. If you want to take a charge from A to B, this will be the work done. Okay, so this is equal to the work done in taking 1 unit charge from A to B. So to calculate the potential difference, we can just do it by using the formula for point charges. And suppose it is asked what is the work done in taking 1 unit of charge from A to B. That will be VB minus VA. Simply just VB minus VA. That is the definition of potential difference. And it comes from, there's electric potential is there. So if you subtract potential between 2 points, that is the potential difference. Any questions? I'll give you more examples.
No, sir.
Okay. So suppose the question is, find work done in moving 1 coulomb of charge from point A to B. So this distance is A. This is also A. And this distance is root 3A. This point is A. This point is B. Okay. So we have to find the work done in moving 1 coulomb of charge from point A to B. Solve this. Got the answer? First find VA, then find VB, and your work done per unit charge is final minus initial potential. Okay, Rishit, let's solve this together. Tell me the value of VA. Potential at point A.
Q square by 4 pi epsilon naught A.
No, we are talking about potential. So potential may we just write the distance between these two. It is not potential energy, it is potential. So Q by 4 pi epsilon A due to the first charge, then Q by 4 pi epsilon naught A with the second charge. Is that clear?
Yes.
Okay. Now, you should tell me what will be the potential at point B.
Q by 4 pi epsilon naught 2A.
Into 2A. Yeah. That is due to the first charge. Then due to the second charge, it is the same. So I can just multiply it by 2. This can be done. Or if you want to write it again, you can write it again. So this will be Q by 4 pi epsilon naught A. Okay, tell me the potential difference. What is the value of VB minus VA?
It is 1 minus Q by 4 pi epsilon naught A.
Minus 4 pi epsilon naught A. Yeah, that is correct. Okay, so this is work done in moving 1 coulomb of charge. If you want to find the work done in moving Q coulomb of charge or Q naught, you'll simply divide this by Q naught. Q naught. It will be 4 pi epsilon naught A. Just multiply Q naught here. Because work done by external agent per unit charge is minus Q by 4 pi epsilon naught A. Okay, now why is this work done coming as negative? So explanation for this can be seen here. Suppose your charge is somewhere here. If your charge is somewhere here, then the force by these two charges will be along this direction. And the resultant force will be along this. This is force due to electric field. So charge itself wants to go from point A to point B. And therefore, you have to apply force in the opposite direction, if you want to move it slowly. So charge itself wants to go from point A to point B. It is going from a point of higher potential to lower potential. Okay, so this is C. This is higher potential to lower potential. So potential difference will be negative. But we can understand it from force also. The force is opposite to the force. The external agent force is opposite to the electric field force because we want it to move very, very slowly. Any questions in this question? Bob, any doubts?
No, sir.
Okay. Okay, there's a small definition. We'll just get over with it. That is the definition of 1 electron volt. This is written as 1.6 into 10 raised to minus 19 joules. This quantity is called electron volt. And its unit of energy. So because the particles, the subatomic particles, the energy over them is really, really small, we like to use this unit, that is electron volt. So it is 1.6 into 10 raised to power minus 90 joules. So it can be defined as like this. This is work done in moving an electron through a potential difference of 1 volt. So if you use this formula, the work done in moving an electron. So you will write the formula of work done by external agent divided by the value E. This will be equal to final potential minus initial potential. If the potential difference is 1, so this will be E into 1 volt. And this quantity is called 1 electron volt. That is 1.6 into 10 raised to minus 19 joules. So this is your work done in moving an electron through a potential difference of 1 volt. Okay. Of course, the charge on this is negative. So you can write minus E here. This will be minus 1 electron volt, minus 1.6 into 10 raised to minus 19 joules. But 1 electron volt is the magnitude of that work done.
Sir, how minus? I didn't understand.
Charge on an electron is negative, no?
Yes, sir. So minus came from there.
Yeah. But we want to write the magnitude as electron volt. So 1 electron volt is 1.6 into 10 raised to minus 19. So that is a smaller unit of energy. This is used for subatomic particles. Any questions? So we have been finding the potential due to point charges. Now, another point charge, 2-point charge system that we know is an electric dipole. So we'll try to find the potential due to an electric dipole. Potential due to electric dipole. See, understand that some of the topics or some of the words that I have used is from your mechanics lecture in the 11th standard. And it is possible that some of you might have not learned that well. But even if you memorize the statements here, that work done by external agent is equal to change in potential energy, And think about it, means whatever work you are doing, means what suppose you are lifting a block of some mass. So whatever work you do, it's common sense that way it doesn't go anywhere. It will be stored as a potential energy in the system. So if you think about it well, you'll be able to understand it. And if you find it faces difficulty, means even then we can discuss those things. But for this lecture, means for this chapter, we need those things to understand it in a deeper way. So potential due to an electric dipole, the first will be again, I will calculate it on the axis of a dipole. So let us say that there are two charge systems. At a point on the axis of dipole. So axis, as you know, is this line. At this point, let us say point P, and this is your center of the electric dipole. This is minus Q, this is plus Q. From the center of the dipole, the point P is R distance away. I'm quite confident that you can do this on your own. So potential at point P will be potential due to minus Q charge plus potential due to plus Q charge. Potential due to minus Q charge will be minus Q by 4 pi epsilon naught. Distance will be R plus L. This distance is R plus L. And potential due to plus Q charge, it will be plus Q divided by 4 pi epsilon naught. And distance here will be R minus L. This total is R, this is it. So R minus L. I'll take Q by 4 pi epsilon naught common. It will be Q by R minus L minus Q by R plus L. Q I have already taken common, so here it will be only 1. So this will be R plus L minus R minus L. That will be 2L divided by R square minus L square. So potential due to electric dipole at a point on an axis is Q into 2L divided by 4 pi epsilon naught R square minus L square. What is Q into 2L? Q into 2L is my dipole moment. So this can be written as P by 4 pi epsilon naught or 1 by 4 pi epsilon naught into Q divided by R square minus L square. Now, if P is far away from O, on the axis, I can write that R is much greater than L. So R square will be, this will imply that R square is much greater than L square. So adding L square to R square or subtracting L square from R square won't have any effect. In that case, we can write the potential of the dipole on the axis will be 1 by 4 pi epsilon naught into P by R square.